Okay, so now let's see it's the problem, the attendance problem in algebra. Yeah, it's the attendance problem in algebra. So it's the first one. We have two matrices A and B, and and in our previous question we know its eigenvalue, and we just consider determinant A subtract lambda I, and lambda I means lambda 0, 0, lambda, these 2 by 2 matrices. And determine A subtract lambda I means for its diagonal entry we should subtract lambda, 2 subtract lambda. And otherwise just KB, this one, its determinant, and its determinant just is equal to 6 subtract lambda, 2 subtract lambda, subtract -1 times 3, so it's subtract -3, so it's plus 3. And then let be 0, And then use the cross method. You could get the eigenvalue lambda equals, 3 and 5. So we have two eigenvalues, 3 and 5. And for each eigenvalue, lambda 1, lambda 2, we have the eigenspace. Eigenspace is this one is the eigenspace of A corresponding to eigenvalue 3, and this one is the eigenspace of A corresponding to eigenvalue 5. And actually, eigenspace of A means the null space of A subtract 3i. The eigenspace of A corresponding to eigenvalue 5 means the null space of A subtract 5i. This one. Okay, and we denote by V1, denote by V2, denote by V2. And since I have already sent you the solution sheet for this question, so yeah, so I think it's fine. Yeah, I have labeled it in the solution sheet. Okay, so now let's see. We have several questions. First one, we want to find a matrix P and a diagonal matrix D1 such that A is of the form. And in this form, you could see P is invertible. You could see that P inverse. So the matrix P is invertible such that A is of the form. And its the form means that here A equals P D1 P inverse. It means that if we multiply by A P in both sides, both right hand side, you will get AP equals P D1 P inverse P. But P inverse P is identity. And any matrix times identity is equal to itself. So it's equal to AP equals PD1, AP equals PD1. And the AP equals PD1 here. So so what's the matrix P and what's the diagonal matrix D? Actually we have this, for this 10 it means that here, let me remind you, what does it mean? If we say V1 belongs to null space of A subtract 3i, it means that A subtract 3i, V1 equals 0. In other words, move it to right hand side, it means AB1 equals 3V1. In other words, it satisfies this equation, right? So that's why we say V1 is a vector belong to null space or eigenspace of A. It means that this one, AB1 equals 3V1. And it makes sense because 3 is the eigenvalue of A. Okay, and of course V1 is non-zero. Yeah, so and another vector V2, so we still have another one. V2 belongs to null space of A subtract 5i. In other words, AV2 equals 5V2. So actually we have these two equations. Okay, so now let's see. So now if we let P be the matrix, so for this question, first one, if we let P be the matrix, first column we consider V1, second column we consider V2, and consider the diagonal matrix D. First entry, diagonal entry, we put the eigenvalue lambda 1. Second diagonal entry, we put the eigenvalue lambda 2. Then, what can we say? For the first matrix, V1 is the vector 1, 3. V2 is the vector 1, 1. And lambda 1 is the eigenvalue 3. Lambda 2 is the eigenvalue 5. Then what can we say? Here, as you see, we have this one. So actually, you will see. Now P is the matrix V1, V2. Right? So once we consider this one, what does it mean? It means that just the multiplication of two block matrices, then we can get it's the AB1 in the first column, AB2 in the second column. This one. But AB1 equals 3B1 is equal to 3B1. And AB2 equals 5B2. 5B2. So what can we say? Yeah, it's a product of this form. Here is our B1, B2, 3, 5. 3, 5. This one. If you check the multiplication, you will see it's equal to this matrix. And now indeed we have this one. Indeed we have this, if and only this one. Okay? Indeed we have this 10. Indeed we have this 10. Since we have this one, so when we consider the product, it's equal to this one. And then now we denote it by P, we denote it by P, we denote it by D1. Then indeed we have this one. AP equals PD1. And it also means that we have this one. We have this one. Yeah, but for this part you could skip it for your exam. For your exam you just need to know for the if you choose the eigenvector V1 here, then it should have the corresponding eigenvalue lambda 1. It should have the corresponding eigenvalue lambda 2 over here. Then it's our D1. Then indeed we have A equals P D1 P inverse. This one. This one. And how about second one? Second one, just once you have this one, it's easy to solve it. The reason is that a to the power of 10. If you check a squared, it's equal to PD1 P inverse. PD1 P inverse. Then what can you say? If you cancel the parentheses, you will see P inverse times P. P inverse times P, but P inverse times P is actually identity. And any matrix times identity is equal to itself. So it's PD1 D1 P inverse. But D1 is diagonal matrix. So when you consider it, when you multiply by itself, it becomes, for its diagonal entry, what's the product? Just in diagonal entry is square length, right? In diagonal entry is square length. So actually it's D1 squared. It's D1 squared. So actually a to the power of 10 is equal to P D1 to the power of 10 P inverse. Here, this form, this one. So and here P1 is the matrix, and D1 to the power of 10 is 3 to the power of 10, 5 to the power of 10. This one. So it's of the form. This one. So it's the second question. The solution about second question. Yeah, so as you see, if you want to know this matrix a to the power of 10, we want to know its eigenvalue. How to find its eigenvalue? Actually, we don't need to really count a to the power of 10, this matrix, first of all. We need, because the reason is that for this matrix A, it's diagonalizable. Since the matrix A is diagonalizable means that indeed we could find a matrix P, diagonal matrix D1 such that this holds. It also, this equation, this one holds means that A is diagonalizable. As we say in class, diagonalizable. And if A is diagonalizable, A is of the form. And A to the power of 10 is of the form. And once A to the power of 10 is of the form, then you could see that these two matrices, they have the same eigenvalue. Since it's equal to, this guy is equal to P D1 to the power of 10 P inverse. So it means that these two matrices, they are similar. D1, these two matrices are similar. They are similar. And in other words, once you consider their eigenvalue, they have the same eigenvalue. So for this matrix, if you want to know this matrix is to the power of 10, its eigenvalue, you just need to know the eigenvalue of A. And for the eigenvalue, just consider its power, its 10th power. Okay. Yeah, so it's the first question and the second question. And now let's see third question. Third question is about the matrix P, B, and we have this one. Okay, so I already see. So we still use the same argument. But now, use the same argument and we could write down the solution directly. So in chapter 6, you should know how to find the eigenvalue, eigenspace, and what's the diagonal matrix D, and what's the invertible matrix P, such that A is the form. Yeah, so it's the third question. For eigenvalue, eigenspace of B, so of course the first of all you should consider determinant B subtrate lambda I. So lambda is the matrix lambda 0, 0, lambda. So B subtrate lambda I, so it's 2 subtrate lambda, 2 subtrate lambda, 1, 1. It's a determinant. And it's equal to 2 subtrate lambda, 2 subtrate lambda, subtrate 1 times 1. Subtrate 1 times 1 is 1. And then it's use the distribution is 4 subtrate 2 lambda, subtrate 2 lambda plus lambda square subtrate 1. So it's lambda square subtrate 4 lambda plus 4 subtrate 1 plus 3 equals 0. This one. And use the cross method, so it's lambda, negative 1, negative 3. Then you will get negative 3 lambda, negative lambda, so it's subtrate 4 lambda. Yeah, so it's lambda subtrate 1, lambda subtrate 3. Lambda subtrate 3. So actually lambda equals 1 and 3. So indeed, the matrix B has eigenvalues 1 and 3. It has the eigenvalues 1 and 3. So it's the eigenvalue. Of B. It's the eigenvalue of B. Yeah. And the second one, eigenspace. So you should check each one. So for example, if we let lambda 1 be 1, then you should check B subtrate lambda 1i. It's null space. B subtrate lambda 1i is null space. So B subtrate 1 times I. B subtrate lambda 1i. So it's the matrix B subtrate I. So subtrate 1. 2 subtrate 1, 2 subtrate 1, 1. And it's equal to 1, 1, 1, 1. And multiply by negative 1, then you will get 1, 1, 0, 0. This one. And the 1, 1, 0, 0 is the variable x1, x2. This one. Actually, originally you should write it down in this way. So originally you should write down in this way. We just leave some part. I mean, 2 subtract 1, 1, 1, 2 subtract 1, 0, 0. Consider the solution set of B subtract Ix equals 0. Solution set of this one. Solution set of this equation. And so you should consider this one. And it's rho equivalent to 1, 1, 0, 0, 0, 0. This one. But for the right hand side, we just skip it. But for the right hand side, we just skip this one. Anyway, so it means that x1 plus x2 equals 0. So x2 equals negative x1. So what's the eigenspace of B corresponding to the eigenvalue lambda 1? So the null space of B subtract I is the say x1, x2 is negative x1. This one. x1 could be any real number. This one. So you could choose one. So you could write in this way. It's the spanning set of. Just choose let x1 be 1. So it's 1, negative 1. This one. So indeed, we could let it be v1. Let v1 be this eigenvector. Okay. And then we still have another eigenvalue. Lambda 2 equals 3. So now B subtrate 3i is equal to B is the matrix 2 subtrate 3, 2 subtrate 3, 1, 1. And it's equal to negative 1, 1, 1, negative 1. And multiply by 1a to second row, you will get negative 1, 1, 0, 0. this one. And again, use the same argument. Here is our x1, x2. So it satisfies this equation, negative x1 plus x2 equals 0. So x2 equals x1. x2 equals x1. So the null space of B subscript 3i is the set x1, x2, x2 equals s1. s2 equals s1. And here s1 could be any real number. And it's the spanning set of 1, 1. You could just choose 1, 1. Of course, you could choose 2, 2, 3, 3, and so on. Okay, non-zero vector is just non-zero vector, then it's fine. Okay, and then we could denote by our v2. It's the eigenvector v2. It's our eigenvector v2. Okay, and then the last one, find the diagonal matrix Q and find the invertible matrix Q and diagonal matrix D2 such that B is of the form. And as we say, if we satisfy this one, it means that BQ equals DQ, D2Q. BQ equals D2Q. So BQ equals D2Q. So just let Q be the eigenvector V1 in the first column, eigenvector V2 in the second column. So Q is the matrix. V1 in this one, 1, negative 1, 1, 1. And the D2 is just let eigenvalue lambda 1 be the first entry, first diagonal entry. Second diagonal entry is the eigenvalue lambda 2. So lambda 1 is 1, lambda 2 is 3. Then we have the form B equals Q D2 Q inverse. Then we have the form. Okay, so it's the first question. Yeah, and here let me remind you one thing. For this question, if you say I just let lambda 1 be the eigenvector 3, and let lambda 2 be the eigenvalue 1, and we could get the same one. And now V1, if we let lambda 1 be 3, then eigenvector is 1, 1. And lambda 2 be 1, then eigenvector becomes 1, negative 1. Then what's the matrix Q and what's the matrix Q and what's the matrix D2? Okay, sorry, here I should correct. I just say, sorry, I correct it. I mean, we still have lambda 1 and the lambda V1 and the lambda 2 and the V2. But if the matrix Q, I choose V2, V1. Choose V2 in the first column, choose V2 in the second column. Then the matrix D2 you choose, it should be lambda 2, and it should be lambda 1, this one. If you consider V2 in the first column, then first diagonal entry you should put the eigenvalue lambda 2. And the eigenvector V1 in second column, then this diagonal entry you should put the eigenvalue lambda 1 here. So if you choose Q as the matrix 1, 1, 1, negative 1, then its corresponding diagonal matrix is 3, 0, 0, 1. This one. Okay. Yeah, it's the second question. It's the first question in linear algebra. Okay. Yeah. So now let's see the second question. Okay, so on Wednesday we have the problem. It's the problem in section 6.2. So we want to solve the linear system. The linear y1 prime equals y1 plus 2y2. y2 prime equals 3y1 plus 2y2. And we have the initial value problem. It's called initial value problem. We have the initial value. y10 equals 1. y20 equals negative 6. Okay, so here, as we say in class, for this linear system, we just give the variable. We just give the variable. Originally, we should write it down in this way. y1 prime t equals y1t plus 2y2t. Here is y2 prime t equals 3y1t plus 2y2t. We just give the variable t. We just give the variable t. As you see here, we let t be the 0. Let t be the 0. Right? Then you have the initial value problem. And for this kind of question, we have a general solution way to solve this kind of question. And originally, its solution for this kind of question, it has two coefficients. But once we give some restriction, initial value for the function y1 and the function y2, then we could figure out the coefficient, these two coefficients. Okay, so now let's see how to solve this kind of question. Okay, so first of all, we denote some notation. We consider some notation. We let y be the vector. First entry is y1. Second entry is y2. And once you consider its derivative becomes y1. In each component, we consider its derivative. And we consider a matrix A. And for the matrix A, just consider the coefficient. Actually, you could view it this way. Just consider this one there. It's something like coefficient matrix. Coefficient first. Yeah. So for the first one, the coefficient is 1, 2, 1, 2. So put in the first row, and the 3, 2 in the second row. We consider its coefficient, their coefficient, and we denote it by A. Then what can we say about these two matrices, these two equations? Could we express these two equations in terms of matrices, in terms of matrix equation, and actually we can. Yeah, you could see that here. What's the here y1 prime? So y prime, it's the y1 prime t, y2 prime t, but y1 prime t is 1 times y1t plus 2 times y2t, and it's 3 times y1t plus 2 times y2t, and you could just use the matrix multiplication again. We often use this here, this one, y1t, y2t, and 1, 2, 3, 2. When you consider their product, it's equal to 1 times y1 plus 2 times y2, 3 times y1 plus 2 times y2, this one. And it's the matrix. And what's this? It's exactly, it's the matrix A, and it's the vector yt. It's the vector yt. So now we have the matrix equation. So for this kind of matrix equation, if we have the matrix equation, y prime here is the node. It's the node. If we have the matrix equation, y prime t is 2 by 1 vector, and even it's not 2 by 2, we have some similar result. But here, if it's 2 by 1, and it's 2 by 1, and then it's 2 by 2, what can we say? First one, we consider that the matrix A is eigenvalue. So if its eigenvalue is lambda 1, lambda 2, and then it has the corresponding vector, eigenvector v1, v2, then what can we say about its solution? Then its solution, general solution. Then for its general solution, y is equal to C1 times exponential lambda 1 times v1 plus C2 is v1 of t. C2 times exponential lambda 2t times v2t. This one. For its general solution. For its general solution, we have this one. we have the general solution. So you should know, actually we have this result. And for the detail, we have explained it in class. For the matrix A, it's lambda 1, lambda 2 is the eigenvalue. It's the eigenvalue of A. And the V1, V2 is their corresponding eigenvector. Yeah. And the general solution YT is is equal to this one. Actually, each one is there. Each one is there. Is its eigen, is its solution. Each one is the solution. And consider their sum is also the solution. And as we said, we have two coefficients. But once we have two restrictions, then you could figure out the constant C1 and the C2. Okay, so now you should consider. So it's our first step and second step. For the matrix A, we should figure out its eigenvalue, eigenspace. Okay, we should figure out its eigenvalue, eigenspace. So consider determinant A subtract lambda I is equal to 1 subtract lambda, 2 subtract lambda, 2, 3. So it's equal to 1 subtract lambda, 2 subtract lambda, subtract 2 times 3, 6. So it's equal to 2 subtract lambda, subtract 2 lambda plus lambda squared, subtract 6. So it's lambda squared, subtract 3 lambda, subtract 4 equals 0. And use the cross method again. So it's lambda, subtract 4 plus 1. So it's subtract 4 lambda plus lambda equal negative 3 lambda. Yeah, so it's lambda subtract 4 lambda plus 1. So if it's equal to 0, then lambda equals negative 1 and 4. Lambda equals negative 1 and 4. So it has two eigenvalues, lambda negative 1 and 4. Lambda negative 1 and 4. So first one, if we let lambda 1 be negative 4, then you should consider its eigenvector. You should figure out one eigenvector is fine. Okay, so one eigenvector, so consider its eigenspace. Yeah, so A subtract negative 1, so it's plus 1. So plus 1i, so it's A plus I. A plus I is plus 1, so it's 1 plus 1, 2 plus 1, 2, 3. This one. And 1 plus 1 is 2. 2 plus 1 is 3. So it's 2, 2, 3, 3. So you could cancel it, right? Multiply by negative 3 halves. And A to the second row, you will get 2, 2, 0, 0. 2, 2, 0, 0. Yeah. So multiply by 1 half, you will get it's 1, 1, 0, 0. So what can you say? What can you say about this matrix? As we know, for its solution say, it's our x1, x2, so it satisfies x1 plus x2 equals 0. Just figure out one eigenvector. So you could just let x1 be 1, let x2 be negative 1, then it's fine. And actually, indeed, you could explain it by this way. A plus I is the solution set of, here is x2 equals negative x1, so it's x1 negative x2, so negative x1. S1 could be any real number, so it's the spanning set of 1, negative 1. Yeah, so as we said, indeed you could let V1 be the vector. You could let V1 be the vector. V1 eigenvector be this one. V1 eigenvector be this one. Okay. And the second one, lambda 2 equals 4. So consider A subtract 4i. And the A subtract 4i is 1 subtract 4, 2 subtract 4, 2, 3. And the 1 subtract 4 is negative 3. 2 subtract 4 is negative 2. Negative 2. And the L multiplied by 1 and A to the second row, so it's negative 3, 2, 0, 0. This one. This one. And we use the notation, it's our x1, x2. So what can we say? It's negative 3x1 plus 2x2 equals 0. Equals 0. So you could choose let x1 be 2, let x2 be 3, right? So for its null space, A subtract 4i. Actually it's of the form 2, 3. But each one we could multiply by t. T belongs to any real number. This one. Actually, for this part, we also could explain by this way. You could let x1 be 1, let x2 be negative 1. But we should multiply by t, so it's of the form. And here, for this one, it's the spanning cell. It's the spanning cell of the vector 2, 3. So, and then now we could do it like our V2. So for the eigenvalue lambda 1, we have the eigenvector V1. For the eigenvalue lambda 2, we have the eigenvector V2. And just plug in the solution. And now we just plug in the solution. Okay. So now we plug in the solution. So now the solution yt equals c1 times exponential lambda 1 negative 1t times eigenvector vt, eigenvector v1. Oh, sorry, there is one thing I should correct it. V1 here, okay, eigenvector v1 is not a function. It's not the function of t. So here is v1. It's exactly v1, v2. Yeah, it's exactly v1, v2. Okay, so the eigenvector v1 is this one, 1, negative 1. Yeah, the function is about here. The function is about here. Here we have the function t. Here we have the function. But for the eigenvector v1, it's just a vector. Yeah, it's just a vector. Okay, and plus c2 times exponential lambda 2, 4t times eigenvector 2, 3. This one. Okay, so what's this? First coordinate. First entry is c1 times exponential negative t times 1 plus c2 times 2 times 1, so we could skip it. And then here c2 times this guy times 2, so it becomes 2c2 exponential 4t. This one. And for this time, it's negative 1 times c1 exponential negative t plus 3 times c2 times exponential 4t. This one. And then now we have the restriction, this one. So y0 is equal to y10, y20, and the y10 is 1. y20 is subtract 6. And it's equal, once you plug in the value 0, you will get, it's exponential to the power negative 0 is 1. Here is c1 times exponential negative 0, so it's 1. Plus c2 exponential. Here is always 0, so exponential 0 is always 1. And if you consider it's inverse, it's reciprocal, it's also equal to 1. So just multiply by 1. And here is negative c1 times 1 plus 3c2 times 1. This one. So what's this? So actually we have c1 plus 2c2 equals 1. Negative c1 plus 3c2 equals negative 6. And consider the summation. You will get cancel it. So 5c2 equals negative 5. So c2 equals negative 1. And plug in the put it in the first equation, you will get c1 equals negative 2, 3. c1 equals 3. Okay, so finally the general solution here. So now finally the general solution yt is this one. C1 here, C1 is this one. Originally is the solution, or you could say this one. But now we should replace C1, C2 by 3, negative 1 respectively. So our C1 is 3 exponential negative t plus 2c2 subtract 2 exponential 4t. And the negative 3 exponential negative t subtract 3 exponential 4t. And it's our y1t, y2t. This vector. And this one is our solution. This one is our final solution. Okay, so it's the solution about our attendance problem in near algebra. Okay.